Wollongong to Sydney. I even enjoy more the drive back to Wollongong. I used to live in Sydney, all right, so I'm being that's an informed or educated comment. So yeah, as I said, it's good to be back up here. We're here for this evening, just the one night, to talk about pneumatic conveying. It's my background area. I did my PhD on this many years ago, and then I expanded my expertise into other related areas of bulk materials handling, which you're covering in this subject. So going into bin design, dust control, dust emissions, dust explosions even. But tonight we're just going to focus on this topic of pneumatic transport. And Ahmed definitely is correct in talking about using air to transport bulk materials. But pneumatic conveying is bigger than that. So we can use other gases, of course. In pneumatic conveying, we also use nitrogen, for particularly where your powders are explosive or explosible. So if your dust can ignite, it can explode, then one way to avoid that is to use an inert gas, and nitrogen is a fairly common gas used for that purpose. So there are other gases used for pneumatic transport. Argon is one I remember many years ago, hydrogen for special jobs, but particularly, and carbon dioxide I believe even. But tonight I'll be mainly talking about air pneumatic conveying systems. Well, that's the most common. But when you're modelling a system, if you want to use nitrogen, your gas constants are very similar, so you can use what you know about air to design a nitrogen system. But when you go to some of the other gases, ammonia gas is another one I remember that comes to mind. The properties can be quite different. You have to be careful. You can't use air properties any longer. So tonight, I only have time really to give you an overview of this topic. I can't go into a lot of detail. Actually, in a month's time, I'll be across in India, in Mumbai, and also Patiala, to do 2 courses on ash handling and pneumatic conveying. Right? And these are sort of 2 to 3 day courses each. And there you have some time to get into some depth, into some design issues. So tonight I can only really provide a brief overview and introduction to the topic. But some of the key objectives tonight, I'll firstly introduce you some of the materials that are conveyed pneumatically, and I'll discuss briefly some of the reasons we do that for those products. And then we'll look at basic components and systems, mainly to introduce you to some probably new terminology that you're not used to in the industry. You will find pneumatic conveying fairly common. Anywhere where powders and bulk materials are handled, we'll see some sort of pneumatic conveying system. In some industries, you'll see it a lot more, in other industries, less. But a lot of the basic components and things that we use there, I'd like to just show you some examples of that, and I'll try and give you industrial examples as we go along, so you know what they look like when you go out into the field. And also introduce you to the different ways we can convey powders and bulk materials using air or gas. We call this the different modes of pneumatic conveying, and this is done for specific reasons, which I'll elaborate a bit later on. And for design and troubleshooting, we'd like to develop what we call pneumatic conveying characteristics. These are essentially performance curves. If you work with fans or pumps, you've heard of fan curves and pump curves. Well, these are product curves. For a given pipeline and a product, we like to generate some performance curves, which we then can use to design or troubleshoot the system. And if you've got this information available, or you can determine it with a test rig, then that information is accurate, and we can use that for those applications. You may have a problem out there, you can maybe justify a bit of extra time and effort and money to determine some of this information, and then at least you're not relying on just simple mathematical solutions. The mathematical models that are out there are not that accurate, depending on how you're conveying the product and the type of product. But if you do some tests on a representative sample in the laboratory, then you know at least that data is accurate for that product. But quite often, if you wanted to do, in the industry, if you want to do 100 tonnes per hour, in the lab you can only do 2 tonne an hour, then you have to what we call scale up the information. And that becomes a challenge in its own right as well. So people like us at Wollongong, Newcastle University, over in the UK, Germany, US, a number of research organisations and universities have been dedicating a lot of time and effort to researching these issues, developing more accurate models, minimising the amount of tests you need to do, becoming more accurate with our scale up or our predictions. So pneumatic conveying characteristics is like a semi-empirical approach to this methodology. And of course we have to have some equations. This is engineering after all. Alright, so that's what we've got in store for this evening. And I understand there's a break around about 7:20, is that right? Yeah. 7:20 for memory from last year? Good? I'm getting trained well. And we don't, in Wollongong it's very rare to have lectures on a Friday evening because we like our football too much, the rugby league. So I don't know why they do evening lectures up here, but we avoid
They
it.
don't like football.
Eh? They don't like football, rugby league. Also, soccer.
We made it so that before that, nobody likes football here, right?
No one likes rugby league?
No.
No one likes soccer?
They like cricket.
Oh, you do like cricket?
Yeah. Yeah.
No cricket this evening, unfortunately. Okay, so I mentioned briefly before about different products we can convey pneumatically. So here we see a condensed list of all the products we've conveyed in Wollongong, and it's by no means complete, that list. And these different products are conveyed pneumatically for all sorts of different reasons. For example, your product may be toxic. And one advantage of pneumatic conveying is it's an enclosed form of transport. We're putting our powder through a pipeline so it doesn't escape to the atmosphere. So in some cases like zinc fume, it may be a waste material, it's highly toxic. You don't want that to get out into the atmosphere. You don't put zinc fume on a belt. A lot of it will disappear into the workplace or into the atmosphere. So that's one reason we use pneumatic conveying if the product is toxic. Or if you've got some food products, like cereal, right? You don't want bugs getting in, so you want to keep the bugs out. So you keep what's inside the pipeline clean, and you then have to design that system to be self-cleaning. You can't have any dead spots, otherwise any food material gets caught, it'll attract bacteria, and you get into salmonella sort of territory. You want to avoid that. So there are reasons for pneumatic conveying. Other reasons, you can look up here, some products may be quite dangerous, like aluminium powder, a project we did many years ago. Some of the aluminium powder is, it's actually just metal aluminium in powder form. It's pure aluminium metal powder. Right, now this stuff is produced for various applications. And in the US, they produce it, or used to produce it, for adding it to rocket fuel to make space shuttle launch more energetic. So it's a highly volatile material. It can be actually 3 times more powerful than TNT. So this sort of stuff, you only need a little spark and it will literally be a pretty dangerous bomb. Right? So you can blow up things pretty easily, even yourself, very quickly. Do not try to do this at home or any backyard experiment. People have tried and they usually either burn themselves or kill themselves or kill someone else. So it's highly unpredictable, that type of event. But under controlled conditions, you can actually engineer something for adding value to a process. So adding more energy to rocket fuel by adding aluminium powder, that's what engineers have worked out in the US. It's also been used in some munitions, adding aluminium powder detonators, some special R&D done in this country as well, not by us. Right, so you can imagine handling that type of material, what sort of procedures you need in place, right, and what we call safe handling. So we can use pneumatic transport for those applications as well. Pneumatic conveying is also used in industries where you need a fairly tortuous path to get from A to B. It may be difficult to use belt or other forms of conveying to run a pipeline is relatively easy, and it's also pneumatic conveying is also used in applications where you'd like to have ease of automation. So if you're looking at developing an automated plant, pneumatic conveying gives you a nice solution. It's a simple solution as opposed to a belt conveyor, for example. Okay, so there's all sorts of reasons there that people use pneumatic conveying, and I'll also touch on others as we go through some other case studies a bit later on. And if anyone's got any questions at any stage, put your hand up. Some people may have experienced some of this stuff already. You might have a question, or if you're not sure about some of my jargon, then by all means, stop me. We'll have a bit of a discussion. Also, this is available in PDF too, I understand by now.
Yeah.
You should be able to download it. Yes?
Coke can be numerically conveyed. Coke.
Coke? Yeah? What type of Coke? You've got to be very specific here. You're talking about that type of pneumatic conveying through a straw? Oh, petroleum Coke. Huh?
Maybe it contains soda.
Soda. As a powder? Liquid. That's more hydraulic conveying than pneumatic conveying. Coca-Cola you're talking about. Soda, soft drinks you're talking about. Yes, a liquid. You can pneumatically pump liquid if you want to, and it's not really pneumatic conveying. It's pneumatic propulsion or pumping, pneumatic pumping. But you usually use a hydraulic pump to pump that. And I'm not covering hydraulic conveying here at all. It's all using gas. Okay?
So which one is this one referring to? Which Coke is this one?
Oh, Coke. Coke. That one, screen petroleum Coke.
Oh, okay.
Yeah. Okay. I mean, you can actually bake coal, like the Coke ovens. You can create Coke from coal. Okay, it's a different type of Coke than maybe what you're used to. All right. Having said that, let's move on. I talked about basic components and systems. There are four main groups that make up a pneumatic conveying system. Firstly, we have the air mover or prime mover. We can use a fan. I'm sure you're used to fans. A blower. You may not be used to blower. It's a positive displacement device, traditionally used to supply gas to furnaces. It's just a little. That's a schematic of a blower. I'll show you later on some pictures. And then also a compressor, which actually compresses the air before we use it. Right, so these two devices don't compress the air. This device compresses the air before we discharge it. So usually fans are used for low pressure systems, but can be for high volume flow rates. So depending on your requirements for flow rate and pressure, we pick an appropriate air mover. What we call the roots type blower. I mean, for a fan, for example, we can go up to maybe 5 kilopascals. Gauge sort of operating pressure or differential pressure, 5 kilopascal differential pressure for one fan. For a blower, you can go up to 100 kilopascals. Right, so that's the difference. But the flow rates are more in the medium range. Fans can go very large flow rate, blowers are medium range. Compressors go to much higher pressures, whatever you want. Typically, for a single stage compressor, maybe 300 kilopascals. Multi-stage compressor, you can go to 600, 700, whatever, thousands, whatever you need. It's very expensive to compress air. And the flow rate range is a lot less again. So depending on your pressure and flow rate requirement, we pick a suitable air mover. How you select those, all different. The terminology is all different, and I haven't got time to go into that this evening. I'll just introduce you some examples to show you the differences. Then we go into selecting our feeder. How are we going to introduce our powder, our bulk material, into the pipeline? How are we going to feed it? How are we going to control that feed rate or flow rate? Different devices available. We can use a Venturi meter, which is nice, hasn't got any moving parts. It's like a suck blow system. You can design one of these with using the old Bernoulli's equation. So if you put air through a converging diverging nozzle, you design that properly, you'll actually get a vacuum at the throat, and you can suck in particles at that point. So it sucks particles and then blows them. But you can only do that up to a certain pressure, typically about 10 kPa gauge here, maximum. Once it goes beyond that, you can't suck anymore at this point, and you blow up the opposite way, which is not good. So these are being used in applications where you've got high temperature or high abrasion, so you don't have to be moving parts. You can make them out of ceramic, so they last a decent amount of time. Not many of them around, but they are out there. Probably the most common feeder is the rotary valve. It's just a little volumetric feeder. You want more product in your line, just increase the speed. So I'll show you examples a bit later on. Then you go into you can feed powders or granules with the rotary valve. Screw pumps are generally for powders, like cement. And the screw actually is a decreasing pitch, which compresses the powder inside the casing to form the pressure seal. And these devices can go up to 200 to 300 kilopascal operating pressure. And if you need more pressure than that, you can go to the pressure vessel, or blow tank, we call it. That's a certified pressure vessel, and that can operate up to 500, 600, whatever you want, 1,000, 2,000 kilopascals gauge. When I talk about pressure units, I talk about gauge generally. There's also gauge units, and there's also absolute units. Okay, so we have to be specific about that, and that's why I always like to emphasise that as I talk about those sort of numbers. Alright, so depending on your pressure requirements, also your product properties, you will select a suitable feeder. And then you need to think about your conveying pipeline. What materials can you select? Mild steel is the most common. We can use stainless steel if you're in the food or chemical industry. Aluminium can be used, copper tubing, rubber hoses, plastic tube. So there's all sorts of different types of pipes and tubes available, depending on your requirements and pressures. We need to select bends. They can be radius bends or different types of bends, T-bends. So again, depends on your product and application. And also diverters. You may need to go to silo A, B or C. You need a diverter valve. And that's not a trivial task. You just don't pick any valve off the shelf. You've got to make sure it's suitable for the product and the application. How you connect your pipes or tubes can be important. Particularly if you've got food product going through there, you don't want simple flange connections, because flanges will be misaligned and you can get a dead spot, which attracts bacteria. So you talk about in this industry, those industries, in food and chemical, CIP, which is clean in place. So the couplings have to be CIP rated, so there's no residual material at those connection points. So you've got a nice smooth bore from pipe to pipe or pipe to bend. If you've got abrasive products, we can purchase wear-resistant materials as well, not just mild steel. We can buy hardened steel, or you can buy basalt pipes. That gets very expensive and very heavy. But there's people go to these lengths to make their pipelines last the distance. All right, so lots of considerations there for your conveying pipeline. And the fourth main area is what you do at the end in your silo. You'd like all your product to go into the silo, back into the process, and you need some sort of mechanism or device to clean your gas, your air. We can use a cyclone, centrifugal separator, but they're not that efficient, particularly with fine powders. So generally we need a filter of some form to filtrate the air, like to clean the air. And so you've got all your air going out and all the particles going into the silo or process. But whatever device you pick here, there's nothing 100%. Filters will get you to 99.99 or something like that, that sort of percentage. It's still not 100%. So if you're pneumatically conveying arsenic powder, of course you can't allow any submicron particles to get out in the atmosphere or workplace. It's logical. It's a poisonous substance. So what you can do for pneumatic conveying, this is one of its advantages, you can take that gas that has a bit of small particle in there, and you can bring it round and put it back into your air mover. You'll still need a filter to clean that air so you don't destroy your air mover. But this way you can have what we call a closed loop system that's totally enclosed. Not many people know, but there is a place in Sydney where they actually have a fully operational gold and silver smelter. Right, they produce 1 gold bullion per week. I'm not sure what that's worth. Use the money, man. How much is that worth these days? You've got them stashed in your
I
garage.
started
haven't you?
doing that long time ago, maybe.
99.9 something percent.
Yeah.
Pure gold. They sell them to the banks, right? And they have a totally closed loop system. You have to. And each week they can they generate 1 can or 1 litre of sludge, like total waste material. Even the product coming out the filter still has gold in it, so they recover it completely. Right? But that's something a lot of people don't realise actually exists in Sydney, the centre of Sydney. It's like Fort Knox. I won't tell you the address. Alright, it's been a long time since I've been there. But, I did manage to get into the inner sanctum. The security is just ridiculous. They also produce silver from that plant. Anyway, so there are your 4 components. If you want to design, operate, troubleshoot pneumatic conveying system, you've got to think about these 4 areas. If you don't do any one of these right, the whole system can fail. So all these things are going to be matched properly to your product and application. So let's move just quickly some examples. So there's a fan, a backward curved impeller fan. I don't know if you do fans in your degree here, but this is normally the sort of fan we use for pneumatic conveying. So this is your suction, air being sucked in and the air scrolls around and gets discharged. So this fan can give you about 5 kPa pressure difference from your outlet. That's the sort of fan that we use for pneumatic conveying. There are other fans around. Axial flow fans are probably what you're used to, or propeller fans. The pressure on those are very poor, pressure performance. These are much better, and they can be used for pneumatic transport. The pipe there for memory is about that big, so it's a fairly big fan, this one. Then the roots type blower, so that's the blower unit there. You've got an inlet, silence and filter there. Air being sucked in and then it gets discharged into there. And then this is just the electrical drive, belt drive system. And this is a pressure relief valve. You can't overpressure a blower, otherwise you'll damage it pretty quickly, overheat it. So you need to set that at the maximum pressure limit rating of the blower. And this is your discharge port here. You connect your pipeline to that for pneumatic conveying. You can also use the blower for vacuum service. Right, so you can suck air through a pipeline and then through the blower. This is for blowing service or positive pressure service. If you take the end cover off here, this is what you see. This is your traditional these things are called lobes, L-O-B-E, lobe, that's the lobe there. We call this a 2-lobe blower, or ears, they look like ears. So that's a lobe, not the lobe of an ear. So it's a 2-lobe blower, and the shafts are counter-rotating. So you'll notice here, it looks like they're touching, they're not. There should be a slight clearance there and there. So when these operate with the pressure difference, they leak internally. And so blower manufacturers, they work all that out for you and tell you what the effective flow rate is for a given pressure difference. They're called blower curves, similar to fan curves. So that's a traditional 2-lobe roots type blower, and a tri or 3-lobe blower. They're more compact, run higher speed, and they're more inherently balanced, quieter, so more efficient than the traditional design. So these days, that's what you buy. But they still do exist. They've been around for decades. This one's a more recent addition to the industry.
What's on the tolerance with those?
Sorry?
What sort of tolerance are we talking?
Clearance. What sort of clearance?
Tolerance,
Yeah, clearance in here, ooh, very small. You need feeler gauges to adjust them. Right, so, and also you've got to allow for thermal expansion because these things run hot, so you've got to allow for all that. So it's got to be properly engineered. And blowers can be quite big, and it becomes more challenging to assemble and fit a blower. So this one is probably one of the biggest that you'll see in the world. And these are used on pneumatic ship unloaders. Pneumatic conveyance with pipes about that big, sucking up a lot of product out of the ship. Again, you need feeler gauges to get those clearances correct. So if you have any metal contact in there, these blowers will self-destruct pretty quickly. Imagine these shafts running at 500 or 600 RPM at that size. That's pretty scary. But it can be engineered, manufactured, precision manufacturing, and you can get it right and allowing for thermal conductivity and expansion. So screw compressors look very similar to a blower. So you've got your inlet filter and silencer, and that's your compressor element, and then there's your discharge tanks and electrical drive, as you can see there as well. The main difference is what you see inside the element. So here we see the traditional 2-lobe blower, the more recent 3-lobe blower. So they're positive displacement devices. They only capture a pocket of air and discharge it. They don't compress the air before they discharge. Whereas in a compressor, let's say a rotary screw compressor, it will capture that air, compress it through the screw, and then discharge it. So if you know anything about the compression cycle, that generates a lot of heat. So you get a lot of hot air coming out of these things. And when that air cools, you'll also get moisture being discharged. You'll reach your dew point. So with compressors, you generally need, for pneumatic conveyance particularly, you need dryers to dry the air. Otherwise you'll get water running through your air lines. I don't know if anyone's in the manufacturing shop, use compressed air, compressed steel tools. Eventually they become quite cold and you'll feel the water running through. You don't want that to go through your pipeline, particularly pneumatically conveying cement with a bit of water in there. That's going to ask for disaster. Anyway, so the traditional type of compressors is reciprocating or piston type, compressing the air before it discharges. And they're still around, but the rotary screw is far more efficient. So you'll see them more prevalent these days. But when you get to really high pressures, you'll go back to the piston type compressor. There are other types of compressor elements, what they call rotary tooth, where it squashes the air before it discharges, like a tooth that comes around and squashes the air. So there are different designs. Most compressors also are oil lubricated, so you will get a little bit of oil in your air. The air comes in contact with your lubricating fluid. And for the food and chemical industries, you can't tolerate any oil, so you have to buy oil-free compressor. And they have to generally be water-cooled, because they run pretty hot. Dry screws are generally used. Okay, let's move on to feeders. So with feeders, I'll firstly start off with the most common feeder that you'll see out there in industry, and that's the rotary valve. So I showed you before a very brief schematic. So there are two main types of rotary valve. There's one called the drop-through rotary valve. And under rotary valve feeders, this is the most common as well. So where your product is free-flowing, like grain, wheat, let's say, or granulated sugar, something like that, where the powder can flow into the rotor quite nicely. You'll see the rotor rotate, the product comes around and then discharges out. Falls out nicely, doesn't stick anywhere. So for free-flowing materials like a wheat or grain, rice, then drop-through rotary valve is generally used. Now if your powder is a bit sticky, then it might stick in there, so we have another type of valve that can be used for that purpose. So for most free-flowing materials, we use a drop-through valve, and there's a typical drop-through valve. You have a round inlet port and outlet port, they're usually the same size. And you can see the blade there. These are called the blades. You can see the blade there, and you can see the direction of rotation. They usually indicate that, which way it's got to be rotating. So this one here, if you're looking end on, will be going that direction like that. Okay, so the product drops in, goes around and drops out. It literally doesn't drop through the valve, otherwise there wouldn't be a valve there. But that's what we call a drop-through valve. So it drops in by its own accord, and it drops out by its own accord using gravity.
That's to control the flow rate of it?
Yeah, so this rotor controls the material flow rate, the solids flow rate. Yeah, so if you want more tons per hour, you increase the RPM of the rotor. So that thing is called the rotor. That's the housing or the casing. And also we have tight clearances in here, usually 0.1, 0.2 millimeters. Right, in bigger valves, you go a little bit bigger. We'll have a look at one of these things being dismantled. I'll show you a demonstration of what we call a demountable rotary valve. This is used, say, in the food or pharmaceutical industries, where they put different products through the valve, and they want to strip the valve down, clean it, and put it back together again before they change products to make sure there's no particles in there. And in the industries required to do that, then they have to do it. So everything here is stainless steel. You can see the rotor rotating, and this is a demountable valve. You can see the rails here, so it's all nice. So you can pull it out. You can see the rotor there. You can pull it around by hand. You can clean. You can pull it right out. Do some nice cleaning, and if you're careful, you can put it back together. You can see the nice tight clearances there. And you can also do the same on the other end, the drive end. And this is also a drop-through rotary valve. And there, this is what we call an open rotor. So there's no end plate on the rotor. You can also buy a closed rotor that's got a closed plate on there. So different valves for different applications, different products. And then hopefully if you assemble it properly, it'll rotate when you turn the motor on. So you need trained people to do that type of work. So you can check all your seals, gaskets, everything, all your clearances are right, and then your valve should operate properly. If you don't do it properly, you'll jam something and the valve will fail. So there's an example of a drop-through rotary valve on a system we looked at years ago. For pneumatic conveying of wheat. So there's your hopper, your wheat's in there. So the valve stopped, there's no product dropping through. So if we want to convey some material, we turn the air on, blow the air through there, start the valve, and powder will drop through the valve into the airstream. Very simple device. You stop the valve, you stop your feeding. And so rotary valve can give you continuous feeding and conveying. As long as the valve's rotating and there's material there, 10 tonnes an hour until something stops. Now, for some products that are a bit sticky, they might not come out. Because you have to understand these wedges, these pockets are wedges. Right? And when you put material in a wedge, you've got friction, and gravity may not be sufficient to overcome that friction or cohesion or sticky adhesion that's in there. So for those sorts of sticky powders, we can actually select a blow-through rotary valve. You can see here we've got the inlet port as before, and we've got the rotor. This is a side view, schematic. And now the pipeline actually is connected to the actual housing. And here the air can blow the material out of the pocket as it gets exposed. As it comes around, the air blows it out. And so the blow-through has been used successfully in a lot of industries where you've got sticky material like your milk powder, it's a bit sticky, a bit fatty. And so just with that bit of extra purging capability, you can clean out your pockets. Otherwise, you'll get some powder sticking behind in here. And when that comes back around, then it reduces the capacity of your valve. So your tonnage will then drop quickly.
But does it collect while it's in operation, or in case you leave it
Does it? Oh, it can happen instantly. Powder can stick instantly in one rotation, yeah. If it's sticky, it can stick. It might build up gradually over time, or might stick very quickly. Depends on how sticky it is. Okay? I mean, some powders you throw against the wall and they'll just stay there forever. Okay? And you need a blow-through valve, definitely. But when you've got a powder that sticky, it probably build up on the inlet port too, and choke your valve too. That has happened. Right there, so there's an example of a blow-through rotary valve. So again, with a round inlet port, you can also have square or rectangular, depends on the manufacturer. And here you can see where your pipe is connected. And your blades are exposed. Right, so if your powder's abrasive, you've got to be careful. Otherwise, you can wear out your rotor very quickly. So I wouldn't use cement through such a rotary valve. Milk powder's not abrasive, so milk powder's good.
Where is the air coming from? Like, what is creating so? From a circular?
Yeah, you've got a pipeline connect. You just use a blower here, blow air through. Or just,
A little compressor.
okay. And then got atmospheric pressure there, blowing, or if you're sucking, this would be a vacuum system. In this case, this is a milk powder factory, and we've got a number of fluidized bottom silos here. One there, 2, 3, 4, 5, 6, a whole bank of them. And you've got all these little blow-through rotary valves connected to the one pipeline. You only feed one at a time. So this one's feeding, the powder's coming through here, dropping down, flowing through here to another silo or whatever. And then we stop that one, then we go to the next one, blow that one through. Okay, then you go to the next one. The other advantage of blow-through is low headroom. Nothing more than that much off the ground. If you've got a drop through, you need more headroom. But you also got to get in there and maintain those things. So you employ small people to get in there to do that work for you. And it's a safety issue, definitely. Anyway, so two main issues with rotary valves I've seen that engineers need to worry about. One is to work out the feed rate capacity of the valve. So that affects your sizing of the valve, selection, and also for the troubleshooting. If you've got a main system, it's rotary valve fed, you're not getting your tonnes per hour. Why? So the first thing you do is check your feed rate capacity, MS, mass flow rate of solids. At the end of the notes, I've got a list of symbols. Everything there is defined. So the equation we use to calculate the mass flow rate of solids, kilograms per minute, kilograms of solids per minute, is a material filling factor times the bulk density. That's dimensionless, that one. Bulk density is kilograms per cubic metre, times the sweat volume of the valve. That gives you so many cubic metres per revolution. That's the volumetric capacity of the valve, times the rotor speed in RPM. So just define everything there for you. So that's the bulk density of the material inside the valve. Sweat volume, cubic metres per revolution. Right, so in one revolution, how many cubic metres does that valve supply? And your rotor speed, RPM. And so if you put those units in here, you'll get kilograms per minute. Now, in the industry, no one talks about kilograms per minute. So you've got to convert to tonnes per hour. Some people talk about kilograms per hour, or those small systems, but generally tonnes per hour. All right, so how do we, the thing that generally the bulk density is known, if it's a given valve, we know the sweat volume. If we're running at 20 or 30 RPM, we know the speed. So then you have to work out what's your filling factor. That's the unknown. That's your material dependent factor. So based on some experimental work out of the UK, in fact, you can see rotor speed versus filling factor for 4 different bulk materials. So you can see immediately your alpha is dependent on your bulk material. So some products will fill your valve pockets quickly, others won't fill that well. So polypellets is a nice free-flowing granular material. You can see the median size here is about 5 millimetres, about that big. That's very free-flowing. It fills your pockets up pretty well. Your You'll notice up here, alpha is about 0.95 up to almost 1. So with that type of free-flowing material, you'll fill up your pockets pretty well. Granulated sugar, I'm sure some of you put sugar in your coffee. So it's about 600 micron, and this one here is 560 microns, about half a millimetre in size. That's reasonably free-flowing. Not as free-flowing as poly pellets. So you can see here, depending on your rotor speed, alpha can be 0.9 down to 0.8 in that range. These are what we call envelopes. So they capture all data. So you get a lot of scatter in your results. So this captures all your data. So you can use that for design. And then poly powder, that's just a plastic powder. D50 is 200 micron. And wheat flour that you make bread from, it's about 40 microns. Now flour varies a lot from mill to mill. So this one's pretty fine. That's a cohesive powder. It's not very free flowing. So here your alpha gets down to almost 0.4. So very high speed valves, it's hard to fill the pockets quickly. All right, so if you were, yes?
What's D50?
What's the what, sorry?
The D50.
It's a median particle size. It's like an average size. Median. So 50% by mass is above or below 5 millimeters. Okay, so it's like a 50-50 split value. So all powders generally have a size range, right? And you can plot that size distribution where the 50% mark is, that's your D50. All right. So if you look at the end of the notes, D50 is median particle diameter. Averages can be weighted averages. If you go to mathematics and statistics, there's different ways of averaging things, depending on your distribution and all that sort of stuff. D50 is, there's no ambiguity to that. D50 is just a D50. Right? If you look up statistics, you'll see D50 there in mathematics, no problem. Okay? Based on any distribution. So, we run an exam in this room, you get a whole spread of marks, you can work out what the D50 is of marks. What's the average mark, so to speak, arithmetic average. Alright? But strictly it's based on the distribution and then where your 50% value is. Then you can work out other things like standard deviation and all those sorts of things, but with particle size distribution we don't do that. We usually work, the main parameter we use is D50, the other one is D10 and D90. So that's where the 10% value is, what the particle size is, and 90% value. And this gives you some indication of spread of particle size, roughly where the minimum is, maximum, and the midpoint. Okay? I'd rather use the whole distribution, it makes it easier. You cover particle size distribution? You should have that. D50? Yes?
Yeah.
Yes?
It's going to be done after this in fact.
Okay, great. Okay. It'll be there somewhere. All right, so just a quick example. So let's look at checking out poly powder with a valve at 30 RPM. So what you would do, you'd go at 30 RPM, go up to poly powder, and you stop at the bottom curve. And you go across and you say, okay, my minimum alpha there is about 0.72. Is that okay? Right? That's a minimum possible alpha for poly powder running at 30 RPM. And then you can go to the top curve at 30 RPM and you can see there the maximum possible value is about 0.8. So depending on what the problem is, if you've got an existing valve, you know the sweat volume, so many cubic meters per rev, right? So most rotary valve manufacturers will tell you what the sweat volume is. The units are generally litres per rev. And then you just divide by 1,000 to get cubic metres per rev. And so for a given valve, given sweat volume, you can put minimum alpha and maximum alpha in here, and you can calculate a minimum possible feed rate and a maximum possible feed rate, which you can then use for design or troubleshooting. And that's how you use this equation. If you're designing or selecting a valve, and you want a certain tonnage, let's say 10 tonnes per hour, you convert 10 tonnes per hour to kilograms per minute. And then you might estimate a RPM. Say you want to select a valve for running at 20 RPM, something like that. So you put 20 in there, you know your bulk density, the 20 RPM you can work out, depending on your product, you can work out your alphas, and then you can play around with the sweat volume to give you that 10 tonnes per hour. So it's a bit more iteration involved with design, but for a given valve, it's a direct calculation. All right, just depends on the application. I'm not going into any further than that, but this is just the methodology we use. And that's the equation we use, and just a quick example to show you. We don't have a one-off number. We give you generally a range, the minimum and maximum. Any questions on that? That's okay?
Yeah.
All right, good. The second issue that you have to deal with for design and also for troubleshooting is air leakage. Rotary valves have clearance. So you've got a rotary valve here, you've got an air mover, and you blow in product from here into a silo, you'll have a positive pressure underneath the valve, above atmospheric. You have QT, well let's define these. So QT is the total volumetric flow rate of air, that's the supplied air flow rate, in cubic metres per minute. Could be second, it's up to you, cubic metres per hour, but in this case it's cubic metres per minute. So that's the volumetric flow rate at this density. So if you've got a certain pressure there and temperature, you can work out your gas density using ideal gas law. I'll show you that later. Alright, so QT is the air supply, and at that pressure there, and that's atmospheric in there, you've got the pressure difference across the valve. So you will, due to clearance, you will lose air through that valve. This is what we call QL, is your rotary valve leakage. It's also cubic metres per minute at the same gas density of rho F I, which is here. We use I for the inlet to the pipeline. That's the feed point. Little e is the exit here. I'll show you that again later. But for the moment, we're focusing here at the inlet to the pipeline. So QT minus QL, so that air, we lose some. That's the remaining air we use for conveying. So the volumetric flow rate of conveying air is QT, the supplied air minus the leakage. It all has to be at the same gas density, in this case rho Fi. Alright, simple concept, you supply air, you lose some, what's left is we use for conveying. Now, is it a concern? Depends on how big your clearances are, depends on your pressure drop and your product. So based on all the work we've done over the years, the amount of air that you lose can be 10 to 50% of your supply air. Now if you end up being at the 10% end, you can get away with it almost. But if you lose half your air up into your hopper, you've got half of your air left for conveying, you may be in trouble. You may not have enough air for conveying. And then you suddenly get a blockage in your pipeline. There's not enough air. So if you don't do anything about it, that's the consequence. Also, the more air you lose, the air wants to go up and the powder wants to come down. So the more air you lose, the less powder will go into the valve. And that will reduce your alpha, as I showed you previously. So leakage also affects your feed rate capacity. So for all those reasons, it's important to determine your leakage somehow. You can ask the manufacturers, you can look up some of my papers, but if you don't consider it, you'll get in trouble. If you make some allowance for it, then you may be on the... It's not an easy thing to predict, so we've played around with it for years. That work I showed you just in the previous slide, that's based from UK, University of Greenwich. We collaborate with them, we've repeated that work and obtained similar results, and they've also done work on leakage. So there's different models around the world, and I'm not going to go into those details, but if it's an issue for you, you need to do some literature search, find some papers that will allow you to do some independent assessment. And don't trust the manufacturers, the suppliers. A lot of the equations they give you, charts, inaccurate. They give you guidance, but a lot of them, I don't know what they're based on, to be honest. We've tested a lot of them, and some Some work sometimes, others don't work other occasions, depending on your product and application. It's very complex. But that's why we did research into it. We found a lot of these models just don't work. And particularly when you go to higher pressures, things go a bit crazy with some of these extrapolations that these models have to be subjected to. All right. Anyway, so that's all I'm going to talk about leakage. And so it's an important issue, and looking at those two issues there, that affects your design and selection process and also potentially troubleshooting. So if you've got a rotary valve system like this and you're not getting your tonnes per hour, it could be due to leakage. Then you have to somehow work out, well, how much leakage is possibly involved to see if it will could be detrimental to what we're doing through the conveying pipeline. So the conveying pipeline starts there at the inlet, and there is the exit. Right. So this is an important part of the pneumatic conveying. That's your conveying route. Any questions on rotary valves? Yes.
Could you just put a venturi underneath that? Do they ever want like put two systems in one go?
Yeah, this is what we call the dropout box or the entrainment box. And this is a very simple design that you see there, which is quite common in the industry. Some people have put a venturi in here to try and suck off the valve, and that will only work up to a very small pressure in here. And these systems operate up to 100 kPa. Those venturi systems won't work. And that can actually, venturi system like that, all it will do generally is increase the velocity here. And if your powder's light, actually can prevent your powder entering the pipeline. I've seen that happen. It was down in Wollongong as a grain terminal. That's in fact what happened. They had a system like this on grain dust. This is part of their dust extraction system, dust control system, and loading ships with wheat. And they had a rotary valve system like this. And they put a venturi in here, and the velocity was so high that the grain dust wouldn't go into it. But the inertia of that was higher than the inertia of the powder coming down into it. So the air won. And so it formed the bridge. And so we put a little bit of just a 2-inch pipe on the back there and solved that problem. Just broke that arch. But that's what a venturi can do. It can be quite negative or detrimental to your feed rate. If it's a low pressure system, less than 10 kPa here, you can get your venturi to work. Like for a low capacity flow system over short distances, you can get it to work there. Yeah. And certainly to minimise leakage, there's definitely advantages there. But it's very limited what you can do there with that technology. Okay. That's a good question. Any other questions? Okay. Let's move on to the second most common feeder is the blow tank or pressure vessel. So this is what we call a bottom discharge blow tank. The inlet port's at the top. That's the silo up here. Drops powder into here. When it's full, we close everything off. We've got an outlet valve that's shut as well in this case. Then we turn the air on, so the air flows through the pipeline. Then we pre-pressurise the blow tank, and then we open the outlet valve, and the product drops down into the airstream and out through the conveying line. So this is what we call a bottom discharge blow tank. The product discharges out through the bottom. You can also get a top discharge blow tank where the product discharges out through the top, as you can see. Right. We still have air coming down here through the fluidising pad. That pipeline actually goes all the way into the blow tank, a couple inches from the membrane, the fluidising membrane. Right, so the pipeline starts here, and then the powder discharges out through the top. You can also, some people go on from the side, we call it a side discharge, less frequent. Bottom discharge, most common, these ones then less common, and the side discharge even less common again. So if your blow tank is down in a pit, and you want to bring your pipeline out, it makes sense to use the top discharge. But I would only use powders for top discharge. If you've got any granular material in there, coarse rocks, I will use a bottom discharge. Alright, so it is product dependent also, whether you use bottom or top discharge. So just to show you different configurations. Now these blow tanks are what we call a batch feeding system. Batch, but one blow tank. So the mass of material we call in there, we call that the batch size. So we might put 1 tonne in there or 200 kilos, whatever it is. That's the batch size. That's what we call a batch blow tank. So with single blow tanks, they're batch systems. So how we operate them is what we call a batch mode of operation. You right?
Yeah.
Okay. Something flying around, is it?
It's about the air conditioning.
Oh, air conditioning. Okay. No worries. Don't ask me.
It's a different socket.
I'm just the messenger tonight. All right. So batch mode of operation means you've got a blow tank, single blow tank. You've got to fill up so many kilos. All right. So that takes time. Then you've got to seal off your blow tank, pressurise it. That takes time. Then you discharge. Then you can convey. Then you've got to wait for things to empty. You stop everything. Then you've got to vent everything back to zero pressure. That takes time. And then you can refill. That takes time. So if you want to, on average, put 20 tonnes per hour into your silo, you may need to convey maybe 40 tonnes per hour through the pipeline, because we have to overcome cycle overheads. So it takes time to fill your blow tank. And while we're filling the blow tank, we're not conveying anything into the bin. So you've got to fill the blow tank, you've got to pressurise, maybe, depending on your product and application. At the end of the cycle, it takes time to depressurise the system and vent your blow tank to zero pressure. Once your blow tank's back to zero pressure, you can open the inlet valve and you can refill your blow tank, restart the cycle. Also, to actuate your valves might take 10 seconds or 20 seconds per cycle. And that may be significant, depending on your conditions. Right, so because of those cycle overheads, we call it, the average blow tank discharge rate can be anywhere from 50 to 100% bigger than the required system capacity. So as I said before, if you want, on average, every hour, 20 tonnes in your silo, you may need to convey at 40 tonnes per hour to make up for the time you lose doing all these things. Right, so depending on your batch size, how quickly you can fill it, all these things affect your cycle overheads. These numbers vary significantly. So you can see that here. So this is a single blow tank unit. Bottom discharge. There's your outlet valve. This is what we call a fluidising discharge cone. So inside we've got a porous cone. Nice technology we developed in Wollongong many years ago, and this improves the efficiency of discharge. And for powder systems, even cohesive powders, this works very well. That's why we install that, use that type of device. Anyway, so when we start the cycle, this outlet valve is shut, the vent valve is open, we open the inlet valve, we fill up the blow tank. It takes a certain amount of time to do that, then we close it. Over here you can see blow tank air pressure versus time, the mass of product in the blow tank, and the air mass flow rate going through the pipeline, the system. So time 0 is when we start our filling cycle, at that point there. So as we open the inlet valve, the product goes into the blow tank, hopefully at a linear rate. You get a nice straight line up to this point, you fill up your blow tank. At that point, we shut the valves off, and then we pressurise the blow tank, pre-pressurise it. So everything's shut. We put air into here, maybe a bit of top air, and you can see here the pressure in blow tank starts to climb. So here you can see a bit of air used for pre-pressurisation. Turn the air on at that time, and then the pressure increases in the blow tank. Now we have a set point. So once we reach our set point, it could be 200 kilopascal gauge, which is that point there. We say we're ready for discharge. At that point, we turn the conveying air on, which is, then you see the air jump up. This is the total airflow going through the system, through the pipeline. Right, and then we open the outlet valve at that point. We make sure this air is on before we open the outlet valve. Because we want our powder or product to go into the airstream. That's the best way to do it. If you're a bit late, turning your conveying air on, you could block the system. So you need that conveying air to get the material started, accelerate the material. Alright, so at that point we reach a steady state condition of airflow. The product in the blow tank discharges, reaches a steady state value, which is that slope, which is nice linear. You have a nice efficient discharging system like that, a nice straight line, and you reach a steady state pressure in the blow tank. So we have a pressure gauge on the blow tank. We measure the pressure in the blow tank. We also put a pressure gauge in here to measure the conveying pressure. Right, so that's your blow batch operation. Now, this all continues happily until we run out of material. So at that point there, we say we're empty. We have a low, can do that by load cell or usually level probe. We say, okay, at that point, we're empty. And then you'll notice the pressure in the blow tank starts to drop because the system's starting to empty out. So your resistance to airflow is reducing dramatically because there's less and less powder in the system. So your pressure starts to drop towards zero. And we leave the air on for a little bit to purge out the pipeline. We get it all out. And once the pipeline's empty, we turn off the air. And at this point, pretty much you're close to zero pressure. And we can also open the vent valve to make sure we have zero pressure. Because we don't want to start refill the blow tank until you reach zero pressure. Otherwise, you will blow up the silo. You don't want to do that. It makes a mess. Right, so once we've reached zero pressure, everything's off. We can refill the blow tank and repeat the cycle. So the overall system capacity down here is the match of the batch size, the mass of the material in the blow tank, divided by all the cycle overheads. So that's the time to fill the blow tank, which is this one here, from there to there. TIP is initial pressurization time, that would be 20 seconds, 30 seconds, whatever it is. The time taken to discharge is from that point to that point, when it's empty. The time to vent or purge the system, which is this time here. And once you're back to zero pressure, at that point there, we can restart the cycle. And we need to add on another 10 or 20 seconds for valve switching. We do that per cycle. You can add 5 seconds here, 4 seconds there, or whatever. I just put the whole thing together, 20 seconds. Most valves you can operate per cycle like that. But some people put a butterfly in there, and sometimes they don't put an actuator big enough, and when you open the valve, it can take a minute. And then you're waiting. So make sure you select your valves appropriately. Alright, you want your valve to open quickly, not a butterfly valve, but a full bore valve, open and close quickly. Okay. Because any valve that you put in there, if it's slow actuation, and if your powder's abrasive, you will rip the guts out of that valve pretty quickly. It won't last long. So you want to open quickly and shut quickly. With the air valves, it's not so critical because it's clean. But when there's powder involved, you want your valves to be full bore. There's nothing in the material flow. And here as well. Some people put a butterfly valve there. If it's cement, it won't last long. Aluminum won't last long at all. Because those valves get chewed out pretty quickly. When they start to leak, you've got problems pretty quickly. So you need the right sort of valves for these sort of service. Any questions regarding blow tank systems, batch systems? No? All happy? So when you get for a single system, couple of 100 metres, 100 metres, that sort of distance, 10, 20 tonne per hour, no problem. But if you start getting up to hundreds, 100 to hundreds of tonnes per hour, or your distances go up to a kilometre or beyond, a single blow tank is not efficient. because it takes a long time for that product to get there. And if you've got high tonnage, it takes a long time, high pressure drops, etc. So for large and or long distance systems, large capacity and or long distance systems, we generally don't use one blow tank. We generally use two. Because you want to keep your pipeline full of product with large capacity and or long distance systems. So for those applications, we need two blow tanks. So for these, this is our old test rig in Wollongong. We ran up to 1.2 kilometres. And for many years that was the longest system in Australia until the power industries adopted this technology and put them in to transport ash away from the power stations. And the biggest system we did up until recently was 1.5 kilometres up in Queensland, 100 tonnes per hour. And there you needed two blow tank system. So while one blow tank is discharging, the other blow tank is isolated and it's being refilled, pre-pressurised, ready to go before the first blow tank runs out. So when this blow tank runs out, we just swap over. And you lose a few seconds. So you don't get quite a continuous feed and hence continuous conveying. You might get about 90-95% continuous, but it's pretty close. You keep your pipeline pretty full of material. So this is what we call blow tanks in parallel or tandem operation. Tandem blow tanks. And you'll notice fluidising discharge cone on the two tanks that we have in Wollongong. So just recently, I mentioned 1.5 kilometres. Just recently we designed, worked with a company called Strata, and now this is probably the longest pneumatic conveying system in the world. This goes 4 kilometres. I was nervous when I designed this. Previously it was 1.5 kilometres, now we've achieved 4 kilometres. This is for a mine up in Queensland. This is the feed silo that tops up the blow tanks, tandem blow tanks as you can see. This is a very unique system. You won't see anything like this anywhere else in the world. And I think there's one system in Europe that was running up to 4 kilometres. I think that's now shut down, so this is probably the longest in the world. And you can see here, there's the 1 cubic metre blow tanks. That's your feed silo. That's your air receiver. Your pipeline comes along here. It goes underground. It goes down to about 200 or 300 metres, and then 4 kilometres underground for underground mine. Right, so that's it. And that system's now been operating all year. We designed it last year, did our test work in Wollongong. So our pipeline is only 100 metres long, 2.5 inch line, and based on that data, we modelled the system, scaled up the model. We developed our pneumatic conveying characteristics from our test rig. We scaled up that information, designed the system, they commissioned it, and it worked very good, according to our predictions. No surprises. And the feed rate over that distance is plus or minus 5%. So very accurate feed rate control. So this is a very special design. I won't tell you how we did it. Not many people can do this. So if you know what you're doing with feeders and pressure and compressed air, then this is what you can achieve. And with an accurate model. That's very important for your pipeline. Anyway, so as I said before, with a tandem system, you get about 90-95% continuous flow rate. Not quite 100%. In some applications, you do need 100%. So this is a system we designed for a boiler, pulverised coal feeding, 100%. You need to be 100%. This was a special plasma torch that was developed, technology in Australia many years ago. Instead of oil firing the boilers, they used coal, and they used plasma torches. And the coal is supplying the fuel for those plasmas to ignite the flame. And it has to be 100% supply. The tandem system is no good. Just that gap of a few seconds is enough for the torch to go out, the burner to go out. So here we have a piggyback system, or blow tanks in series. You need 2 tanks again, but this top small one is like an airlock. This is your main feeding vessel. There's your discharge pipes, that's a top discharge system. So that pipeline runs across here a couple of 100 metres into the boiler, goes around, got multiple feed points. And so this is running 100% all the time. So when the level in here drops down, this valve is shut, this one has been refilled under atmospheric conditions. We shut this, pre-pressurise, we balance the pressures, we open the valve, and that powder then drops into the main feeding vessel. And it refills the blow tank, close it off again, we vent this, refill it, vent it again. Just like an airlock system. And so while we're filling, this thing's continually feeding at 100%. Right, so you can achieve 100% when you require, but you need more headroom. You need a blow tanks in series, piggyback blow tank. Any questions? Alright, so the main difference is the tandem system. This discharges, then I stop that and then discharge the other one, so it's in parallel, right? Whereas piggyback is like that, in series. So you know, in electrical systems, you'll know about parallel circuits and circuits in series. Alright, it's the same thing. Any questions about that? Alright, just quickly before we go for the break, a very quick slide. Oh, sorry, question there. Yes, sir.
When you're in the piggyback system, so when you're repressurizing and clearing out the material, is it 100% clear or some of it less?
Yeah, so all the material here drops down under gravity. So we've got the pressure balanced here across the valve. So when we open that, the powder drops down under gravity. Right? And then once that has fully discharged into the bottom vessel, we then close that valve again. And then we vent that to your silo filter. And then that goes back to atmospheric condition. And we can refill it, make it ready for the next cycle. When that material level drops again, we make sure that one's ready to drop. Okay, and then we just balance the pressures again. We don't want any sort of residual pressure across that valve. Otherwise, you might blow a little bit of air that way or blow it that way, and it upsets your feeding accuracy. Okay, so you can see the pipe here, this is your pressure balance line. So this system here, we actually used a combination of pressure vessel and rotary valve to give you a feed rate accuracy. So we're using rotary valves in application not designed for this sort of service. So there are tricks of how we pressure balance across the valve to do that. Because valves are generally up to 100 kPa, but this system with a valve, rotary valve, is running up to 500 kPa, no problem. But you have to know what to do with the pressure balancing. Can be all done if you work out with all your basic engineering principles. And we'll do a bit of that after the break, some of the basic calculations that we perform for pneumatic conveying. All right, just finally, before we go to a break, the last aspect of your conveying pipeline is, what bend do we pick, what diverter. And I'm not going to spend any more time just to show you. Here we've got radius bends, we can go to T-bends, all different types of bends. Bends give us flexibility, but two issues with bends. One's wear, every bend will wear, so there's maintenance issues, and every bend produces pressure drop. So the more bends give you flexibility, but also you need more energy or more pressure loss to overcome. Alright, so it equates to kilowatts and power, right, and dollars, running costs, compressor side, blower side. So all these things do add up at the end of the day. So my general golden rule of thumb here is minimize the number of bends. They give you flexibility, yeah, but you can overdo it, so be careful. And also, T-bends will give you a higher pressure drop than a radius bend. Right? And also with diverters, this diverter will work well in a chemical plant with plastic pellets. If you put that into a cement plant, it'll be a disaster. And you can buy diverter valves for the cement industry, and they work quite reliably. You put them into a chemical plant, it'll be a disaster. So it's product dependent and flow dependent. So in general, for bends and diverters, right, you need to think about the layout of your plant. These things are bigger than other diverters, so what dimensions are available, etc. So your plant layout is important. There are different types of diverters, different types of bends, so you need to think about all what's available. look at your pressure drop of each component in a T-bend versus radius bend, or a plug diverter versus one of these big ones, or a parallel bore diverter. If you've got a abrasive product, right, these bends will wear out faster than a T-bend. But T-bends have higher pressure drop than a radius bend. So it's always a juggling act. Right? But if you don't allow for these, your system will fail. Your bends will wear out quickly, or you don't get the capacity because your bend pressure drops are too high. So wear rate is important to consider. And also if you've got an abrasive product here going through this, it'll rip the guts out of that pretty quickly. So you've got to be careful. You've got to pick the right component for the application of the product. And it's very product dependent, as I said before, with these diverters and the bends. And particularly if you've got a pharmaceutical application or food, where you normally use radius bends and you can't use T-bends. So it's very application dependent, and also how you convey your product, well, whether it's dilute phase or dense phase. So that also will affect what components you need to pick. So it's definitely not a trivial task when you're selecting your bends and diverters. You need to put a fair bit of thought into it to make sure those components are matched properly to the product and the application. If not, your system will fail. All right, so after the break, we'll talk about how the different modes of pneumatic conveying. So we'll take 10 minutes.
10 minutes will be enough.
10, 15 minutes, okay? About 1:30, we'll try and get back underway. I noticed quite a few people from India here. Of course, this might be interesting for you. But more, so I've been running a few of these courses now in India, and I collaborate, actually my last PhD student, Shama Malik, his home base is in Kolkata, and but now he works at Patiala, Par University, this one down here. So it's a private uni, and I'm glad he went to that type of university because they're quite more liberal about doing these sort of commercial ventures. Very hard with the state funded universities to do that, like the IIT. So it's been quite easy for him to set up a laboratory like we have in Wollongong. And so my first PhD student did that. He went back to China, did business, so we do a lot of business in China because I can trust him, they're good friends. And I can trust this guy, we're good friends, and he's now doing the same sort of business in India. And he really wrapped up over 5 years. He's done that very quickly, and now he's got a new laboratory running. So together we get people from like NTPC, the big power companies, attending these courses, and I think it's quite unique. I don't think anyone else is doing this in India. So last year we ran also in Jaipur, so we've got to take the course around India. So we're back into Patiala this year because of his new laboratory. Just to show you, so I go to India quite a bit. Actually, as you can see, I'll be going over there shortly. And then also after that course, we run another one in Mumbai for 2 days. That's the in-house course. I forget the name of the company, but it's a big company, manufacturing company in India. Yes?
Did you go every year?
Yes. Yeah. We run 1 or 2 courses. Also every 3 years, we run an international conference. Last one was 2 years ago, so the next one's due next year. And I encouraged him to run it in Kolkata, but because of the new laboratory, he's going to run it back in Patiala. So he's running Patiala twice, Jaipur, next one in Patiala, and after that be in Kolkata. And so there's a lot of industry in Kolkata region, around that region, power, etc. And anyway, so just to show you sort of things we're doing globally. I don't expect anyone here to attend that next. All right. Okay, so talk about the different ways of pneumatic conveying, the different modes of conveying. Pneumatic conveying has been around over 100 years, and the original systems are dilute phase, and that's actually the most common form of pneumatic conveying. A suspension flow, we call it. Dilute phase, lean phase, sort of terms used in the industry. And so you give enough air to to the pipeline of the particles, and you'll suspend the particles, and you transport those particles from A to B. And I don't know how to put a number to it, but maybe 80% at least of systems in the industry are like this. Relatively easy to design. Most of your pressure loss is due to air. So you predict your air pressure loss. You can maybe even add on a percentage to allow for your particle losses. But once you get the higher and higher tonnages, the situation changes, and your product becomes more a dominating factor. Anyway, so that's suspension flow or dilute phase flow. And then in more recent times, when I say recent, last 40, 50 years, people develop fluidized dense phase conveying for powders such as cement, fly ash, pulverized coal. So we can, even through a 100 ml pipe, we can do 100 tons per hour, these types of materials. So it's high concentration flow, it's lower velocities, and if, in a way, in terms of transport efficiency, it's much more efficient than this, maybe 10 times more efficient. So you're transporting a lot more product per unit air. But generally with higher pressure. The dilute phase is relatively low pressure, this is relatively high pressure because of the high concentrations. So the pressure drops here are due more to the powder property than the air. So the situation completely changed. This is the dominant phase here is air, the dominant phase here is your powder, your particle. Then for granular materials, such as wheat, rice, plastic pellets, muesli, any granular material like this, we can convey what we call slug flow. And these slugs are formed naturally by the material. We get the air velocity right, these slugs form naturally. So we can convey these materials very gently, down to 1 metre per second, half a metre per second, if need be. And why do we do that? It's to maintain the integrity of the material. The particle may be fragile, and we can convey those particles without damage, or even segregation. Up here, if you've got an abrasive product, or wide size ranging material, you'll damage the particles quickly, and it also segregates during flow. Whereas this one is used for specific applications in the chemical and food industries generally. So for granular materials, we can do it in a slug flow. For cohesive powder, you need some device to break up the material, and you can create cohesive plugs. So we call this plug flow. So the main difference is between the slug and the plug is the trail left behind the slug. This is really high-tech terminology. Right? But this is terminology I developed. Because some people around the world talk about plug flow being that and that. But they're fundamentally different. How they behave and how you model and design them are fundamentally different. The mechanisms are different. All right, so I needed to come up with different terminology. So one night I was outside at night, sitting down thinking about this, and I saw a slug go across the footpath. I said, yep, I'll call this slug flow, because it leaves a trail. And that's a true story. Okay, so, but overseas they won't know what I'm talking about. But slowly this is happening around the world. In China, as I mentioned, and through India, they talk about slug flow now. And people, what are you talking about? Putting slugs down the pipe? Yeah, well, you'll see what I mean when you see the videos in a moment. Anyway, for cohesive powders, we like full cream milk powder, cocoa powder, high fat contact material. We can create plugs over short distances, and you get these little sausages coming out the end of the pipe. Then you get into crushed ore, crushed coal, bauxite, crushed bricks. We can convey a single slug per cycle, so we call that single slug conveying. So those materials, the only other form of pneumatic conveying is dilute phase. Because these materials suited here can't be done this way. So if you start conveying rocks in dilute phase, you need very high velocity, and it doesn't become practical. So you can, for short distances, 100 metres, 200 metres, and for low tonnages, 10 tonnes per hour, something like that, you can convey these nasty materials quite well. Crushed coal, crushed rocks. My first consulting project was in 1983, I remember, and it was single slug conveying of diamond ore aggregate for the Argyle diamond mines. And we designed about 12 pneumatic conveying systems, took about 3 million in the deep end, and all those systems were installed. We put pressure vessels in with wear liners, replaceable wear liners. So, 3-inch quartz rock going through a pipe pneumatically is unheard of, but we did it. And the reason they picked pneumatic conveying for that project? Prior to that was all belt conveying. But the only reason they wanted pneumatic conveying was security. Right? Because in the plant they had belts running with diamonds on them. And they didn't want to subject their workers to the temptation of stealing diamonds. This is true. So they wanted to put everything through a pipeline, so they didn't want to subject our workers to stress of being tempted to stealing diamonds. And that's why they picked pneumatic conveying, and also because it's easy to automate. And they've still got a couple of those systems running, apparently, up in Argyle. Yeah, interesting. Anyway, abrasive 3-inch quartz rock, pneumatically conveyed like this. And it worked. Some products like alumina, you take bauxite, refine it, you get a white powder, you put it into a smelter, smelt it, you make aluminium. So alumina is a raw material for aluminium production. Right? So we have a number of smelters around Australia, up in Queensland, down in Portland, Victoria, and they get the white alumina in, and it's a gritty material, gritty. So for gritty materials like alumina, another one is PVC powder, plastic powder. Another one is a sand, at 100 micron sand, D50 100 micron. So those sort of powders almost go this way and almost do that, but come back at this mine and it goes unstable. So these powders still can go into this sort of dense phase mode, but we need some assistance. So we can provide the assistance with an internal bypass to keep the slugs under control, or an external bypass to keep the slugs under control. Right, and it's very application dependent which way you go. So if you've got like a chemical product application or pharmaceutical, something like that, you can't use the internal bypass because some material can be left in the tube. That's not allowed. So you have to use a clean in place system like an external bypass. So depending on the application, we go one way or the other. So these materials with an assistance can be conveyed still efficiently in a dense phase mode. And then extrusion flow is a fairly specific application where your product may be a bit wet, and you fill up the whole product and you're pneumatically pumping it basically through, the Americans call this salami flow, and the whole thing just comes out like one big sausage at the end of the day. And you can convey very under control conditions, we did a project for the pet food industry, conveying in a power, the dog food with gravy, the meat lumps, and also for cats' whiskers, the fish chunks in gravy we conveyed like this. Very specific application, was more pneumatic pumping than pneumatic conveying. But there's no moving parts. It was a pressure vessel, pipeline, and there was no damage to the product. So with mechanical pumping systems, you can damage the particle. It's a quality control issue. So it's a very specialised application, but it was done. We got the, I haven't got time to show you that, but it was an interesting project where we've actually, we were thinking about bringing all the pet food to Wollongong, but we thought about the potential of bacteria and the smell in the lab. I didn't like to think about after a few weeks what the lab would smell like, with pet food lying around everywhere, meat going off, can you imagine? So it'd be like your rubbish bin after a few weeks of not cleaning it out. It'd be that sort of smell. And said, no, we'll send the test rig to site. That's what we did. And we commissioned everything on site. Did the test on site. Anyway, so it was an interesting project, very specific application. So all these ones here we call dense phase. That's dilute phase. And anyone in the industry knows what that is. And dense phase can mean one of many different things. And so when people talk about dense phase, you should say, excuse me, what do you mean? This one, this one, this one, or this one, or this one? So we need to be specific about what type of dense phase. right? And you know, it's quite often you see a nameplate on the pneumatic conveying system that says dense phase pneumatic conveying system. Okay, people believe it. You go and listen to the pipeline, that's dilute phase. They say, no. The nameplate says dense phase. I said, hey, rubbish, have a listen. It's dilute phase. So people spend the extra money to buy a dense phase system, and the supplier hoodwinks you into thinking you got a dense phase, but it's a dilute phase system. And the reason they do it is because these are much easier to design than these systems. So if you want a dense phase system, you pay extra money, make sure you get one. And you just got to listen to the pipeline. That's all you've got to do. You'll hear the slugs going through it. You hear the fluidized dense phase. It's easier to keep going. The heavier it is, the more it wants to drop to the bottom of the pipe. But if it's designed properly, it'll be a self-cleaning system. Okay, so I talked about before feeders, air movers, the pipeline, different modes of conveying, and what do we do at the end of the pipeline when we go into the bin? So one option is to put it through a cyclone. So you can get cyclones fairly efficient, maybe up to, depending on the product, 98 to 99%. But you still have a small percentage of dust coming out through here. And these days you can't blow that to atmosphere, of course, so you still need some filter, generally, here. And so what people tend to do these days is just do that, not worry about cyclones. But still people use cyclones for specific applications, and maybe as a pre-cleaner, and knocks out most of the product, and then you have a filter handling the fine material at the end of the day. Or if, depending on the application and your tonnages, etc., you can just have a small filter like that on your bin. And so when it cleans, it drops the product back into your process. So that's like what we call the insertable filter. So I haven't got time to talk about filtration and how we design these things, select them, but generally with the more stringent emission requirements placed on industry, we require filters everywhere. So you've got to size and select these properly, and particularly if you've got a hot product or hot process, it needs some special attention. And so you've got to work out the maximum airflow through the system, work out your filtration velocity, and then you can size your filter appropriately. And you've got to pick the right filter material for your powder. If your powder is really sticky, smeary, like detergent powder, you need a bigger filter. If it's grain flour, or grain dust I should say, that's generally easy to filter. So again, depends on your powder property, what you do here with your filter. And if you don't do the right homework on it, your system will generally have a chance of failing. Or you might blind up your bags prematurely, and you have to end up changing all your bags out frequently. It gets expensive. Particularly if you've got a bag house, you've got thousands of filtered bags, it gets extremely expensive. And the other issue with filters, you have to be careful if you've got an explosible dust in here, you've got an electrostatic spark in there, you can generate an explosion very easily. So you have to buy even more expensive conductive filter bags. Right? So carbon impregnated bags that are earthed, so it doesn't generate electrostatic charge. So this is the world we live in. Right? And you see examples in Australia, there are more examples overseas, where the standards are not as stringent. Right? I can show you some disasters that have occurred, people dying because of dust explosions. Because dust explosions, when they happen, they generally happen unpredicted. It's an unpredictable event. It gets out of control. And if you haven't got the controls in place, your safety management plan, you can destroy entire factories very quickly, within seconds, if it gets out of control. That's where proper design engineering is paramount to the success of your long-term success of your plant. Sustainable operation, okay? Not just emissions to the workplace and the ambient, but also protecting our personnel and equipment on site. Doesn't matter what industry you're working in, petrochemical, chemical, food, right? All these things have to be dealt with properly. Anyway, so So this part of the business is also very important for all those reasons. And so again, it's not trivial, you've got to do it properly. So the general thing I can say here is yes, we need some sort of filtration in our business. All right, let's talk about systems. So let's bring it all together again. We talked about all those components individually. Now we want to bring the whole thing into a pneumatic conveyance system. So this is a typical schematic of a very simple positive pressure or blowing pneumatic conveyance system. So we have an air mover there, that can be a fan, it could be a compressor, it could be a blower, taking air from ambient, delivering it to a pipeline. So there's your feeder, that could be a rotary valve, that could be a blow tank, any of those other things I talked about previously. So that's your feed bin or supply bin, that's open to it. Atmospheric conditions, atmospheric pressure I should say, that'd probably have a filter on it too to keep it contained. And then you supply product into that bin. And then that feeds through the pipeline and gets delivered to silo 1, 2 or 3. And you'll notice we've got diverter valves there to achieve those multi-destination operations. And then we have a filter. We can have a filter on each bin, or you can try and match them up at one central filtration system. I prefer this, each system separate. So these are called the receiving bins, these are your feed or supply bins. So when I talk about the conveying pipeline, it's the part of the pipeline that does the conveying of the particles. So that starts at the feed point. Also we talk about that being the pickup point. That's where the particles are picked up by the air and transported. So that is the inlet to the conveying pipeline. We usually use little I for inlet pipeline. Now the conveying pipeline starts there. Now if we're conveying to silo 1, that's the end of the conveying pipeline when we're conveying to silo number 1. When we fill up silo 1, we go across to silo 2. So we change our diverters, and that becomes the end of the conveying pipeline when we convey to silo number 2. So the conveying pipeline is getting longer. And the maximum length for design is the silo number 3. And we should always check the minimum length as well. Make sure things are still going to work nicely for us. Alright, so the conveying pipeline, you can see horizontals, verticals, bends, etc. We have other pipe work connected to our system. So we have what we call air piping. So from the feed point working upstream to your air mover, that distance can be a few meters, it could be hundreds of meters, depending on your application, where your compressors or blowers are. Right? So maybe your air piping losses are small, or maybe they can be significant. So we've got to allow for that. And surprisingly, based on some work we've done in India, a lot of the power stations there with their ash handling systems, a lot of the engineers have overlooked the losses due to the air piping. And some systems are 200 or 300 metres long. That's a few kilopascals, 50 kPa loss across the air piping system. And then they didn't have enough pressure available to get the tonnage they need through the conveying system. You know, it's just ridiculous that people overlook the importance of all these bits and pieces in the system. So you've got to look at the big picture. You've got to make sure all components are dealt with, including the air piping. Anyway, so sometimes it's important, sometimes it's not. So in terms of another bit of terminology, if we talk about the conveying pressure of the pneumatic conveying system, that's the pressure just before the feed point, as close as we can get it. So we can actually measure that on site. So we can put a pressure tapping in there, put a pressure gauge, and that is little PFI. So I indicates the inlet to the conveying pipeline. So that's your inlet conveying pressure, or simply conveying pressure. Now we can also put a pressure gauge at the end of the pipeline, normally on the bin, and that becomes the gauge pressure at the end of the pipeline. Now for this system, that will be essentially 0. If this is a hydraulic system, which one's bigger, VFI or VFE? Hydraulic system, liquid. Sorry? VFI.
The same.
So who says, okay, I won't go through those. There's three options again, but I won't go through those. It's the same, because hydraulic systems, liquid's incompressible. So VFI equals VF equals VF, velocity of fluid. It's constant. In pneumatic conveying, it's never constant. So which one's bigger? You've got to understand, in pneumatic conveying pipeline, the air always expands in the direction of flow. So I'll ask again, which one's bigger? Who's for VFI? Okay, who's for VFE? Right, majority wins. VFE is always bigger than VFI. Okay. We'll test you in the next slide too. VFE is always bigger. Air always increases down the pipeline for a single diameter pipeline. It's constant diameter. Because you have to understand the pressure here is above atmospheric pressure, the pressure here is zero. So the air will expand through that pipeline, the velocity will increase, reaching the maximum VFE. So the maximum air velocity is always at the end. Alright? Okay, I'll prove it to you. I'll show you later how we prove that, if you're not sure. We'll come back to that. Alright, but anyway, why would we pick a positive pressure system like this for an industry application? Alright, the main reasons are operating pressure. So if we want a couple of 100 kilopascals across this pipeline, you can only do it with positive pressure. You can't do it with vacuum. What's the maximum pressure we can achieve in a vacuum system? What's the maximum pressure drop we can achieve in a vacuum system? Think about it. 50 kPa? 100? 150? Is there a limit? What's absolute vacuum? Don't know. The maximum you can achieve is minus 100 kPa. That's it. That's it. No more. Okay. Right. So atmospheric pressure on Earth is about what? 100 kilopascals. What's the pressure in space? 0. There's your difference. In vacuum, that's the most you can achieve with any device, any suction device. Do we run up to 100 kPa vacuum? No. Because once you get to 100, nothing's there. Nothing's left. Gone. Alright? So the maximum limit for a vacuum system is generally about 80 kPa between start and finish. Usually we'll limit to 50. Alright, so if you want 200 kPa difference from start to finish, you can't do it by vacuum. You have to use positive pressure. You have to compress the air more to give you that pressure available for conveying. Okay? Alright, so anyway, so pressure, when your pressures go above 100 kPa, you have to go to positive pressure. You have to do a blowing system. Also, plant layout. So if you've got multiple destinations, the best way to do that, the most efficient way to do that is with a blowing system. With diverters, as you see. Very hard to do that with vacuum if you're sucking into 3 different silos. Very difficult. Okay? You can do it, it's more complex. Alright, so any questions about that? Positive pressure systems. The problem here, of course, is everything's compressed air, right? Compressed gas flow. So gases expand, right? And we're using that expansion through a confined diameter to give us that velocity increase, which is desirable but also undesirable if it gets too high. So we have to keep that under control. Yes? Is that a question or just a fiddling of the pen? Okay. All right, let's look at vacuum service now. This will really throw you into the woods. Okay, so now we've got the air move at the other end. Now we're sucking through the pipeline through our receiving bin, and our air move is over here, usually a fan or a blower for vacuum service, or we can use a vacuum pump as well. Okay, so now we can feed from A, maybe rotary valve there, or B, or both, depending on what you want to do. You can design these things accordingly. So for this system, that is our maximum conveying pipeline. Alright, that's the feed point, that's your end point. So in this system you have air piping a little bit at the beginning here, you have a filter, so usually to stop bugs and mice and things like that being sucked up through the line. And here we have a bit of air piping between the filter and the air mover. And again, that might be a short distance, or that may be quite a long distance. So if we're talking about putting a pressure gauge on here, what would that read? That pressure gauge. What do you reckon? Yeah. If it's because you're sucking in air from ambient, there might be a small pressure drop across this, not much, but the air pressure inside that bit of pipe there is pretty close to atmospheric pressure. So the gauge pressure is 0. If I had an absolute pressure transmitter there, I'd be reading atmospheric pressure. But most gauges we use are gauge pressure units. Okay, so that's why I talk about kPa gauge as opposed to kPa absolute. So I'll put a pressure gauge there, and that'll give me it's going to be pretty close to 0. And PFE at the end of the pipeline will be a negative pressure. So I've got to put a vacuum pressure gauge there to read negative. So it might be -20, -30, -40, something like that. Kilopascals gauge. Right, pressure drop, we use the same equation. The pressure drop across that pipeline is PFI minus PFE. So PFE might be -20. So 0 minus -20 is 20. So delta PT is 20 kPa. So when you talk about pressure difference, it's just kilopascals. You talk about a static pressure, you talk about gauge units. Kilopascal gauge. Doesn't matter whether you're talking about pneumatic conveying or pneumatic circuits or hydraulic systems, you do the same, use the same language. Alright? It's not just pneumatic conveying, it's other applications of that. Alright, but that's not the complete story as far as pressure is concerned, because generally with a vacuum system, the pressure drop across the filter is more. It could be 10 kilopascals. And so, let's say this is a blower, we might say that that's the inlet vacuum pressure of the blower. We put a pressure gauge there. This might be reading -20, that'll be reading -30. And that's the pressure we need to size that blower. Right? Because that's the maximum pressure difference across the blower. So if you ignore that filter loss, you may be out with your blower selection. You've got to make sure you calculate that air piping loss properly and also your filter loss properly. Alright, so as far as the conveying pipeline is concerned, though, it's still PFI minus PFE. It's the same equation. Any questions on that? Alright, so why would we pick up, with the velocity again, VFI at the inlet, VFE at the exit. Alright people, I convinced you last slide, which one was the maximum? Which one's the maximum here? VFI or VFE? Okay, who's for VFI? Who's for VFE? Who doesn't know? Hands are changing. Hands are changing. Now what did I say last slide? The maximum air velocity is always at the end. So the correct answer is VFE. So whether you're blowing air through a pipeline or sucking air through a pipeline, the air will always expand in the direction of flow. Air velocity will always increase in the direction of flow. Doesn't matter what the pressure difference is. 10, 20, 30, 40, 50, your velocity will always increase in the direction of flow.
But what about the material velocity?
That will also increase. Yes.
Proportional to the air velocity?
Yes. Your powders, fine powder, it will get pretty close to the air velocity. Vacuum, you've got to be really careful. When you get up to 50s and 80 kPa differences, you don't have much air left, and your velocities just go through the roof. Now, there's a project I did in New Zealand, lactose pneumatic conveying system, the sugar powder thing. It's not abrasive. They had a vacuum system. And they were running at 80 kilopascals. And I did a simple calculation, had this horrendous wear problem. And steel pipes wearing out in a matter of hours. I couldn't work out why. So I worked out the airflow from my blower, had the pressure difference, and I calculated the air velocity at the end here was 150 metres per second. The maximum air velocity we usually use for pneumatic conveying is about 20 to 25. I had 150. And later, I'll talk about wear and velocity. It's horrible what happens at those numbers. And I said, look, I can give you a simple solution. I said, what was it? We just stepped the pipeline at the end. We increased the diameter of the pipe, and we dropped the velocity down. We got it down to about 40 metres per second, something like that. Yeah, wear problem disappeared. Yeah, the last bend is always the one that wears out first. That one will wear out first. Yep. And in the last system, this is the bend will wear out first. Remember that. The last bend will wear out first. And that bend usually is on the top of the bin, on the silo, up in the air, and you can't get to it. And that's the first bend that will wear out, because the velocity there is the maximum. This bend will be the last to wear out, because that's the first bend in the system. So a few little things to remember about pneumatic conveying. Velocity always increases in the direction of flow. As a result, it's the last bend that will wear out first. Good final exam question. Which bend will wear out first? It's a 50-50 option.
Yeah, but it's own book exam, so no point to a theoretical question.
I'm sure the questions will be harder than that.
Yeah, it is.
All right. Anyway, why would we pick in industrial application a vacuum system? All right. Well, one would be plant layout. So if we've got multiple feed points and a single destination, the best way to do that is a vacuum system. So we can suck up from different feed points and bring it to a central destination. That's one reason. Another reason people use vacuum, and it's written in the literature, if you look it up, if you're handling a toxic material, they say, oh, pick a vacuum system, because if you have any leakage, it's all internal. It all gets sucked into the pipeline. So if we get a wear point here, the air gets sucked in, so we don't lose particles. And that's reported in the literature. And it makes sense. Is it true? No. So don't believe everything you read just because it's reported in some journal. Check it out for yourself. Right, so I put a big question mark against that, because here we see a vacuum pipeline. And we see the beginning of a wear hole. Particles are being sucked up through here. Particles impact at that point, and that's where it's going to wear out first. Air is being sucked through that hole as it's wearing bigger and bigger. But particles are still escaping, as you can see. Now, luckily, these particles aren't toxic. But if this was a zinc powder or a lead powder, we have a big problem. Because we've got those particles then can be dispersed to the atmosphere. A bit of wind, people breathe that in. So it's not 100% safe. But then you have to ask, why do we lose particles? Well, there's a complex answer to that, but the simple answer is physics. Because your particle inertia is bigger than your air inertia being sucked into the hole. Because particles have velocity, they have inertia going around that bend, and they will shoot through the hole due to physics. And the air's being sucked in, but the particles are heavier, and they get past the air, no problem. Alright, so this issue here is questionable. You cannot rely on it 100%. And there's the proof. Those particles have come from that hole. It's quite obvious. Okay? So don't always believe what you read out there, so be careful. Anyway, so minimum conveying velocity. So you'll see for a range of bulk materials, this is all for dilute phase. This is the air velocity at the feed point. So if we're using a positive pressure system, you can see the pickup velocity we need for dilute phase. varies from, in this case, 14 or 12 metres per second up to 25. Generally, the heavier the material, the more air velocity you need to suspend it. All right. Okay, so we can see the numbers depend on the product, which is fair enough. But when we go to vacuum systems, the feed velocity is also higher than the positive pressure system. Why? Again, the answer is physics. Because you have to understand a couple of basic things. This is a vacuum system, right? When we drop particles down there at 10 tonnes per hour, we've got a certain momentum of particles going that way, and to pick up those particles we need a certain momentum of air. Right? Momentum balance to get the thing going. Now with a positive pressure system, let's go back to this one, the mass of air coming through here is a lot higher than if we're just sucking with ambient. So if the mass of air is much higher, to get the same momentum, we can get away with less velocity. So momentum balance. So if the mass of air is less, the velocity of air has to be higher. And hence, for a vacuum system, the air velocity at the feed point needs to be higher. If you take the average of that divided by that, it's almost a factor of 2. So the starting velocity for a vacuum system is higher than the equivalent positive pressure system. And so if you've got an abrasive product that you want to put through a vacuum system, be very careful. Because if your starting velocity is higher, your exit velocity is going to be even higher. So your air velocities here might go from 30 metres per second up to 50 or 60. Here you might start at 15 or 20 and going up to 30. We can work with that. But these numbers can get ridiculous if you don't design it properly. So what does this mean from a wear perspective? So if you're looking at wear, air velocity versus wear rate. Well, this is the service life of the bend before the bend fails. So we're pneumatically conveying sand under dilute phase conditions over different velocities. So what this experimental curve shows you, for example, at 24 metres per second, which is a typical dilute phase number for sand, we convey 10 tonnes of sand before the bend fails. If we drop our velocity to only 15%, to roughly 20 metres per second, we double the service life of that bend. So the relationship between wear and velocity is not linear. It works both ways, increasing or decreasing. So the relationship based on it for a wide range of materials is something like this. The wear rate is proportional to velocity, roughly cubed. Alright? It ranges from 2 to 6, typically 3. If you don't know anything else, use 3, an average of 3. So let's assume that wear rate proportional to velocity cubed. Now, if our transport velocity is increased by a factor of 2, how much higher is the wear rate? 8 times, correct. So we've got a good mathematician down here. 2 cubed is 8. So your vacuum system will wear rate 8 times faster than the positive pressure system. It's an important consideration if you want your pneumatic conveying system to last the distance. Alright. So if you've got an abrasive product and vacuum, be careful. You're going into dangerous territory. Your velocities, your wear rates are going to go through the roof. Okay, so be very careful. Alright, I might skip this section and go to our tutorial. Or the equations. Alright, so the important equations we're going to go through, and the remaining time we have, we'll go through a bit of an exercise. So the continuity equation, you remember that from fluid mechanics? Yep, alright. So air mass flow rate of fluid, the air mass flow rate in kilos per second, equals the density of fluid times the velocity of the fluid times the cross-sectional area, rho VA. Or you may be more familiar with just density times volumetric flow rate. So if you use SI units, you can't go wrong. You'll get kilos per second Over here you have kilograms per cubic metre for your gas density times cubic metres per second for your volumetric flow rate. Or here, that will be metres per second times metres squared, your flow area, and so you still get kilos per second. Alright, that's your continuity equation. Now how do we use that for pneumatic conveying? Well, we generally design on a steady state condition. That is, when your airflow is constant, your mass flow of solids is constant, and your pressure drop is constant. That's what we mean by steady state. So when we have steady state conveying, everything's constant. Your air mass flow rate through the pipeline, through the system is also constant. So we can say that MF is a constant. That's good. I like things when they're constants. Alright, so when MF is constant, we can say MF equals the conditions at the inlet of the pipeline are equal to the conditions at the end of the pipeline. So rho VA at the inlet equals rho VA at the exit. Continuity is conserved.
Density would not change.
Density does change. We talked about that before. The gauge pressure at the inlet of the pipeline is equal to is different to the gauge pressure at the end of the pipeline. The pressure drop across the pipeline is PFI minus PFE. Alright? I'll show that in a moment. So how do we calculate the gas density? We use the ideal gas rule. So the gas density is the absolute pressure divided by RT. Right? Absolute pressure is the gauge pressure plus atmospheric. Right? So if you've got a positive pressure system, you may have 50 kilopascals gauge at the inlet, so we put 50 there, plus 101 is 151. Absolute units. Right. The pressure at the end of the pipeline could be 0 plus 101, which is atmospheric pressure. Right. So you can, so mass of air is conserved, right? Unless you've got a hole somewhere. Don't have our holes operating on a pneumatic conveying system, otherwise you lose powder, or right, somehow. So anyway, so assuming that you don't have any holes, rho VA at the inlet equals rho VA at the exit. Yes?
Does the temperature change from the initial state to the state?
That's a very good question. Does the temperature change? Well, the answer is no. Pneumatic conveying, for most cases, is isothermal. It's nice. Temperature's constant. I like constants in this business. Come on, engineers, we've got to keep life simple, don't we? Okay, got to keep it as simple as we can. Try and keep our constants always there. Alright, so rho VA is constant, yes, but what does change in the pneumatic conveying system, we know the velocity changes. And why does the velocity change? Because the pressure changes. And if you've got a single diameter pipeline, AI equals AE. You can cross these out. That means rho V is constant through the pipeline. Rho V at the inlet equals rho V at the exit. So if the velocity at the exit is the biggest value, the density at the exit is the lowest value. It's atmospheric density. Alright? And for vacuum it's the other way around. But don't forget, in the vacuum system, the velocity is the maximum at the exit, and the density also is the lowest. But the density there is less than atmospheric density. You're sucking is below atmospheric pressure. That's why we call it a negative pressure system. Blowing is positive pressure, sucking is negative pressure. Now, for pneumatic conveying, we convey kilograms of product per kilogram of air or gas. We call that M star. So M star is non-dimensional, and it's MS, tons per or kilograms per second of solids divided by the kilograms per second of air used. So it's a measure of transport efficiency. So for dilute phase, that number is typically 5 or 10 kilograms of product per kilogram of air. For a fluidized dense phase system, it can be 100, 200, 300 kilograms of product per kilogram of air. It shows you how much more efficient fluidized dense phase is, for example. All right, just throw some numbers out there, give you an idea what these numbers look like. Pressure drop for the system is made up for a pipeline, given pipeline and product and velocity. Total pressure drop across that pipeline is due to air and solids. Now in this subject, we're only going to focus on this bit. We're not going to do the So the air pressure loss, we can use Moody diagram to work out our friction factor. You've done friction factor losses? Yes? Liquids or gases? I don't know. Doesn't matter. You get your friction factor from your Moody diagram. Yes? Some people nodding, they remember Moody from a distant relationship. Well, that guy, maybe you don't know him because he did his work back in 1949. He's probably dead now. But Moody is the guy that invented the friction factor chart based on Reynolds number and roughness and all that stuff. Okay? So Moody, that's what Moody is. He developed a friction factor chart we use for fluids and gases, liquids and gases. So that's your Darcy friction factor, rho v squared on 2 times the length of pipe divided by the diameter. So this is the pressure loss for frictional losses. Bend losses you have to add extra. We're not going to do that here. Right, now solids pressure drop. There's still people doing research around the world to try and come up with better models to predict solids pressure loss. And we're not going to do that here. Alright, so you can ignore that part, this equation if you like. This just says that's a function of your solids friction factor coefficient, solids loading and all these other complicated factors. So we're not going to go into that here. But this one we know we can use Moody and do some calculations. And for a dilute phase system we can do 90% of our design already. And all these symbols are in the end of the notes, which you see here. So all of those symbols are defined here that you've got in your PDF. Everything's there. Should be there. If I've forgotten something, let me know. Right, so everything's there. So for example, N star, MS divided by MF. MS is mass flow rate of solids, MF is mass flow rate of air, etc., etc. Okay? So remember that chart? Moody? Yep. So you need your Reynolds number. There's your roughness of your pipeline. So you go up to roughness, go across, you get your lambda from that, your friction factor. For pneumatic conveying systems, for commercial piping, it's typically around 0.02. If you don't know anything else, you just assume 0.02, you're going to be pretty close. It generally varies from 0.015 to 0.025 in that range. Because Reynolds numbers are usually in a particular range, and the roughness is in a particular range for commercial piping. And if you have put a bit of a region in there, you'll find the average is about 0.02. Alright, so that you can calculate every time. And we've got a little example to go through. Any questions, sir? Yes?
To go back regarding where in the bends.
We're in the bends, yes?
Do you have any method for like monitoring this before failure, or just wait until it happens?
Just wait it happens and you've got you've got a problem then. But usually if you've got a toxic mixture you can't wait. So you've got to do NDT testing, thickness.
Yeah.
You have to go around and check your bends, which sometimes is necessary. But generally most people don't care until it's a problem.
And then
Then it's too late.
it starts going on.
And then you get the duct tape out and the elastic and the... I can show many examples. Anyway, so if we design our system properly, it shouldn't wear out that quickly. Right? But you can't, it's one thing about wear and wear rate, you can't predict anything like that. You have to do the tests and work it out. Absolute prediction of wear and service life is almost impossible. It's too complicated. Alright, so this is a bit of a tutorial we have at the end of the notes. And so all the questions are there, but you don't have the answers. So I'll try and give you those answers as we go through. In the time we've got left, 20 minutes, should be able to get through most of it. Anyway, question 1. Consider this very simple positive pressure system. Right, so we've got product going from a feed, a rotary valve, dropping into it. We're going to ignore any air leakage losses and stuff like that. Anyway, we've got air going through this pipeline, 100 mil diameter, 90 metres long. So we've got VFI there, VFE there. So which one's bigger? VFE. Yes. Good. Not bad for a Friday evening. Okay. Alright, pretty good. I'm impressed. Alright, so we've got poly pellets being conveyed. You know, those 5mm pellets I talked about earlier. We've got 10 tonnes per hour going through this pipeline. And the pressure drop across the pipeline is 50 kilopascals. Right, so we put the gauge, if we put a pressure gauge on our bin, what's it going to read?
0.
At the back? What's it going to read? Pressure gauge here. gauge here, what's it going to read? Yeah, 50 kilopascals gauge. So 50 minus 0 is 50. That's equal to delta PT. Delta PT equals PFI minus PFE. PFE 0. So we can ignore filter losses for that system. For this one. Alright, so you can see there, PFE, I even got the answer there, equals 0. I forgot I put the answer there. Anyway, atmospheric conditions. So if I put in my ideal gas equation, if I put 101 kPa absolute in there, divided by RT, and R is there for air, as my gas constant. It's probably a little bit different what you learnt in fluids. This is how we do it in pneumatic conveying. You use specific volume, which is 1 over density, alright? We use density here. Right, so if you put 101 divided by RT, you get a gas density of 1.2. The air in this room, 1 cubic metre weighs 1.2 kilograms. Very close to that. Pretty close to what, 20 degrees, wouldn't you think? Yeah. Atmospheric pressure, what do you reckon? Have you checked your barometric readings today? 1010 hectopascals is the correct term we use for atmospheric pressure, which is 101 kilopascals. It goes up and down, depending on what cyclones are around and low pressure things and all that sort of stuff, right? But average 101, typically, at sea level. If you get 1 kilometre above sea level, it's different. It changes. Right? But at sea levels, we use 100, typically. Anyway, so at atmospheric conditions, the gas density is about 1.2. Alright, anyway, so that's just the question, or the information for the question. So the first question is, let's calculate the conveying air mass flow rate. So what's, I'll try and do this. Alright, what's the continuity equation? Okay. That's my little squiggle row. Now, this is steady state conveying. Our airflow rate's constant, our pressure drop's constant, the tonnage is constant. So under steady state conditions, we can say that equals constant. And that's equal to rho Fi. That's from that previous slide, alright? That's the continuity equation. So the question asks, what is MF? So we're after, that's what we're trying to find. So we've got to look through these equations. This equation, what things do we know? Yeah, we know the area. So we can say separately, AI equals AE equals pi on 4 on 0.1 squared. I've got my calculator here, but that's easy to calculate. I'll let you work that out. Okay? The diameter is 0.1 metres. Okay? So the diameter is 100? Yeah, 100.1 metre. So use SI units. So we know AI, we know AE. Do we know VFE?
Yes, no, VFI. That's good.
Oh, we're given VFI, aren't we? The minimum pickup velocity at the feed point is 19.2. So we know VFI. Now we've got a better chance using the first equation, don't we?
Yes.
Now the question is then, can we determine rho Fi based on the given information?
Yes.
Okay, so rho Fi is, we'll use the ideal gas law, right, is capital the absolute pressure at the inlet, which is the gauge pressure at the inlet plus atmospheric pressure. Right? That's the absolute pressure at the inlet. my pipeline. Because if you put what you've got to do, think about this. What we're doing really is putting a pressure gauge there, and that's going to read 50 kPa, right? 50 kPa gauge, and we've got to convert it to absolute units. So we've got to add atmosphere to it, 101. Okay? Divided by RT. And be careful, we've got to use SI units. So for my pressures, I've got to put pascals in there. So that's going to be 50 kilopascals gauge, which is 50,000 pascals, plus atmospheric pressure, which is 101,000. So this numerator is 151,000 pascals, absolute pressure, okay? 151,000 divided by 287.1, and capital T is, so it's 20 degrees plus 273.15. Okay, that's the correct definition. And it's isothermal, so this is a constant. So if you calculate all that, that'll be pretty close to 1.8. So the gas density at the inlet of my pipeline is 1.8, the gas density at the exit is 1.2. So you can put this, it'll be 1.795, close enough to 1.8. So we know now what rho Fi is, times 19.2 times that will give you MF. Right? So you'll get 0.271 kilograms per second in that calculation. Now the second question is, what's the solids loading ratio? So M star is simply MS divided by MF. And M star is dimensionless. So if we use for MF kilograms per second, we must use kilograms per second for solids as well. Now MS is what? 10 tons per hour, metric tons per hour. All right, not American tons per hour, that's a different number again. But in this business, it's always metric tons unless specified otherwise. Okay. So 10 tons per hour, we've got to convert to kilos per second. The simple conversion is divided by 3.6. Okay. Or you've got to do it the long way. Multiplied by 1,000, divided by 3,060, all that sort of business. All right? So you divide by 3.6. So you'll get 10.3 after that calculation. That's a typical number for dilute phase suspension flow. 10 kilos per kilo of air. It can be less than that, not often bigger than that. So you've got to understand that M star. Now, another question for you. Is that M star a minimum or a maximum? Think about it. Look very carefully at the things that are highlighted in the question. Is M star a minimum or a maximum? Minimum? So you're saying that we can convey more kilos, so we can convey more product per unit air. Saying? So that's what it means. If you're saying it's minimum, I like the conviction, that's great. You've thought about it, so that must be a minimum, because you see the word minimum up there. But don't forget, the minimum is in the denominator. So if the minimum is in the denominator, that means that's a maximum. M star, alright? So when you say this is the minimum air velocity, that means that airflow is the minimum. That means N star is the maximum. In other words, if we convey more product than 10 times per hour for the same airflow, we're going to have trouble. Or if we convey for the same product flow rate, less air, we use air mass flow rate, say 0.25, we're in trouble. We get deposition. Alright, so read the question carefully, check the information carefully. This is a minimum conveying velocity. So this airflow that we calculated, air mass flow rate, is a minimum mass flow of air you need for 10 tonnes per hour of this product through that pipeline. So if we exceed M star, either increasing product flow or decreasing airflow or both, we're going to block the system. We haven't got enough air to sustain the suspension of those particles. Okay? That's what that word minimum is all about, and that's very important for question 2, which we're not going to get to. But anyway, we'll make sure that everyone's happy with what we've got so far, that we fully understand all those issues. Yes?
How do we know how much length do we need?
Well, that's usually determined by site.
Because
100 metres of pipe, 90 metres of pipe in this case, we've got 90 metres there, that's a site information.
Yeah.
That's usually defined by someone else.
Oh,
Okay? Someone else will tell you that. Because, someone's building a plant, I'll put a processing plant there, they'll put the silos over there. Okay, we'll keep the distances as short as possible, but in this case it's 90 metres.
so it's not about the questions, it's about testing for the length.
Oh, okay, for testing the length, it's whatever you can get in the... We'll try and pick the biggest and longest pipe to match the industry, but the industry is always a lot bigger than what you can put in a laboratory. Right? You try and put a 1.2 kilometre pipeline at UTS, where are you going to run it? Down the goods line?
They can loop.
Go around in circles?
Yeah.
Up on the roof somewhere? We had the same problem in Wollongong. So especially on campuses, you don't have, everyone fights for space. You try and put a pipeline somewhere, you've got to disguise it, make it look like an architecturally designed fence.
Yeah, that's nice.
That's what we did. We got away with it for many years, until someone worked out it wasn't a fence, it was a pneumatic conveying system. Anyway, that's the problem. And if you've got luxury of campus space, you can do it. Anyway, so when we rebuilt our lab, we couldn't put our big pipeline in anymore. But we don't need it anymore, so we've done all that modelling work. And that 4 kilometre system proves that what we're doing is working, so that's good. Anyway, so you're happy about 10.3 being a maximum. I mean, that's a separate issue, but just make sure you understand that. Right? Because that's important for question 2, how you answer that. Anyway, so let's move on. What else we got here? Calculate the superficial air velocity at the end of the pipeline and the percentage increase of VFE with respect to VFI. We know VFE is the maximum. What is that maximum? Well, at this point in time, we now know that. We know that. Do we know rho FE? Or can we calculate it?
Yes.
Yeah. Rho FE.
It's 101 because yes.
Perfect, 100%. Okay, 1.2 kilograms per cubic metre. So that one's 1.7, close enough to 1.8. You can use a calculator. I know those numbers off by heart, but anyway, 1.8 compared to 1.2 doesn't sound a lot, does it? There's actually a 50% difference in mass. Right? That means a 50% difference in velocity. Really? Roughly. Physics. Anyway, so atmospheric density is what? So we know now what, we know this one, so we can easily calculate VFE. We know everything else. Okay? So find VFE, and you get 28.7 metres per second. Right, so the air velocity starts off at 19.2 and it increases steadily up to 28.7. And that is almost a 50% increase, as I indicated before. If your gas density changes by 50%, your velocity will also increase by 50% due to continuity. Rho v is constant, remember that, okay? Because your A's can cancel. AI equals AE. Is that all right? All right. Okay. Any questions on that? The rest of this is simple calculation. I don't think we need to spend any more time unless you've got a concern. The third question is using your Moody diagram. But before you do, to work out your air-only losses, so we're going to calculate your pressure loss of air, delta PF, using the equation I showed you before. So to do that, we need to get our friction factor, lambda F, which we get from Moody. To do that, we need Reynolds number. But to do that, we work with our mean conditions. So you firstly need to calculate the mean superficial air velocity for the pipeline. So for that pipeline, what's the mean superficial air velocity? How would you calculate that? I'm sorry? That's what most people will do. They'll say VFM equals VFI plus VFE divided by 2. Unfortunately, that's wrong. Because what you're doing, you're naturally assuming that the velocity increases linearly through the pipeline, and it doesn't. Rho v is constant. That's a hyperbolic function. I think. Is that the right mathematical term? I can't remember the mathematics. Anyhow, rho v is constant. It's not linear, right? So, how do we calculate VFM? The answer to that question is we do it by continuity. So the way we do it, and then continuity is conserved. We say that equals rho FM. AM is the same as AI and AE. Okay? So rho FM, VFM equals rho FE, VFE equals rho FI, VFI. So what's rho FM? Is the mean gas density. Inlet is 1.8, exit is 1.2. What's the average? 1.5. You can do a bit more accurately on the calculator, right? But just the process you go through. You take the average of rho FI and rho FE, the arithmetic average. That's fine. Then you use continuity to work out the corresponding mean gas density. Now you could do it the other way. You start off with VFM equals VFI plus VFE over 2. And then you go back to continuity to calculate rho FM, but that logically doesn't make sense because you talk about a mean pressure of a system. And we can actually do that very quickly because you have to understand, the gauge pressure there is 50. The gauge pressure there is 0. What's the average pressure? 25. The absolute average is 126. You can work out rho FM immediately.
So you're sure that the pressure moves linearly?
Yeah, so well, we'll just calculate an average pressure, the average of two numbers, that's all. And then we calculate the corresponding gas density. Now, in incompressible flow, you don't care any of this. This only affects compressible systems, gas systems, where the pressure difference is more than 10 kPa. Because beyond that, things become non-linear. Below that, you can assume linear and you get away with it. Okay? But don't forget, use continuity. You can't go wrong. Because you're obeying physics. Right? Any questions on that? Alright, so we're running out of time here. I'll give you the answers for that. So, VFM, if you go through this process, is 23.05 metres per second. If you want, calculate the average of those two velocities, 19.2, that one there, and 28.7, and it's not equal to that number. It's a little bit different. The bigger the pressure drop, the bigger those differences. Anyway, so you work that out. You can work out then your Reynolds number. And Reynolds number is constant through the system because it's isothermal. That's lambda F from your Moody diagram. So you've got the Moody diagram in your notes, you can use that one. And then you put your numbers into the equation on the previous slide and you should get 6,800 pascals using SI units again. Alright, so that's question 1 completed. And that's about it. So the only thing I will give you, only take 1 minute for question 2. I'll give you the answers, so if you want to take a photograph, that's fine by me. in the notes, you'll have this, but without the answers. So the answers are there. So in working out the equivalent vacuum system, you've got to there's two ways you can do it. You can assume the same pickup velocity and you'll find out you're wrong if you make that assumption, because your n star ends up having to be more than what you had before. You can't achieve 15. Maximum is 10. We talked about that before. So this is wrong. This is right. If we assume the same air mass flow rate, our vacuum system will work. Our pickup velocity, you'll notice, is a lot higher than 19. It's now 29. Exit velocity is getting up to 57 metres per second, assuming the same pressure drop. And that pressure drop is going to be wrong too, because although velocities are higher, your frictional losses are going to be higher. So vacuum systems can go out of control. And that's the proof. For a simple system like this, it's only over 90 metres. Okay? And that's all I've got time for this evening. The answers are there. You can have a play with that. If you can't get any of those numbers, send us an email.
It's going to be a part of the assignment. I will give you this question as an assignment. Okay?
Good. And there's a couple of little extra ones. There's no real numeric answer for that. It's more of a discussion. All right? Which one of these assumptions is correct and why? The answer is physics, but you can't give that answer in the assignment. Physics is always the answer.
Yeah.
And my problem now, I have to exercise physics to get back to Wollongong. All right? So thank you very much for your attention.
Thank you for coming.
Thank you.
Thank you.